Can you hear me? Anybody please respond?
Yes, ma'am.
Thank
Good
you.
morning, ma'am.
Good morning.
Good morning, ma'am.
Next heading, applications of equilibrium constant. Is it clear what is written on the board? Applications of equilibrium constant. Number one, to predict the extent of the reaction. Number one, to predict the extent of the reaction. Number two, to predict the direction of the reaction. Number three, to calculate the equilibrium concentration. To calculate the equilibrium concentration. To calculate the equilibrium concentration. Okay, first one, to predict the extent of the reaction, how much the reaction gets. How much the reaction gets over. By looking at the equilibrium constant value, whether the reaction is almost completed, this reaction will be going to almost completion, or it is remaining at the starting only, or considerable amount of products are also obtained. These are the things we are looking forward. Number one, whether the reaction can be completed almost fully, or the reaction not yet moving, it is still at the starting position only, products are not getting formed, or considerable amount of products are also formed. So for that we are first checking to predict the extent of the reaction by looking at this Kc value. By looking at the Kc value, that is number one, you write, if Kc is greater than 10 to the power 3, if Kc is If Kc is greater than 10 to the power 3, that means reaction almost goes to the completion. Write down, Kc is very large. If Kc is greater than 10 to the power 3, Kc is very large, the reaction proceeds nearly to completion. The reaction proceeds nearly to completion. Almost it gets completed. For example, H2 plus Cl2 gives 2HCl. Its Kc value is 4 into 10 to the power 31. 4 into 10 to the power 31. See, very big value, greater than 10 to the power 3. That means such reactions get completed almost fully. That means the reaction proceeds nearly to completion. Now, if Kc is less than, number 2, if Kc is less than 10 to the power minus 3, if Kc is less than 10 to the power minus 3, write down, the reactants predominates over the products. The reactants predominate over the product. But this case is very small. The reaction proceeds rarely. Your case is very small. The reaction proceeds rarely. For example, N2 plus O2 gives 2NO. One example, that is N2 gas plus O2 gas gives 2NO gas. 2NO gas. What's the problem? Anybody said Lakshita is unable to enter. Lakshita Jara. Kc, here the Kc value is equal to 4.8 into 10 to the power minus 31 at 298 Kelvin. See, very small value. The reaction proceeds rarely. Means reaction nahi chalega. If you are starting, it will be at that starting stage only. You are not going to get the product. So by looking at this Kc value, you can talk about whether the reaction will be completed, we will be getting the products, or whether the reaction is not moving to the forward direction, so we will not get the products. If Kc is in the range of 10 to the power 3 and 10 to the power minus 3, that is a third. Then appreciable amount of reactants and products are present. If Kc value is in between 10 to the power minus 3 and 10 to the power 3, write down, appreciable amount of reactants and products are present in the equilibrium. For example, H2 plus I2 gives 2HI. 2HI. This Kc value, Kc is equal to 57. 57 means 5.7 into 10 to the power 1. So Kc is in the range in between 10 to the power minus 3 and 10 to the power 3. Such reactions are also good, but this below 10 to the power minus 3, such reaction is better not to conduct such reaction, because you will be spending your money and time and you are not going to get any product. So you can, looking at the Kc value, you can predict the extent of the reaction, how much the reaction can proceed to give the products. Next, to predict the direction of the reaction. To predict the direction of the reaction. For example, I am giving A plus B gives C plus D. C plus D. Now, you consider a big amount, with the reactance amount will be very large, reactance amount will be very large during the reaction, means at the starting of the reaction, at the starting of the reaction, reactance amount will be very large. That time no C and D, 0, 0. As time passes, as time passes, some C and D will be seen. Suppose after 5 minutes, A got reduced, B also got reduced from coding. Accordingly, little bit. In the beginning, let this much A and this much B was there. So here, no C, no D. After some time, A amount got reduced, B amount also got reduced. So little bit of C and little bit of D you can see. After some time, again A got reduced, B got reduced. So little bit of more C and little bit of more D you can see. Suppose, okay, after some time again you are seeing A is reduced, B is reduced, so you are getting a little more C and little more D. And suppose equilibrium is reached. At this time, equilibrium is reached. Equilibrium is reached. So, here only we can see Kc. You can see Kc at this position only. This to the power, for example, C and D, this is B and A. At this position, you can talk about Kc. Kc is equal to this concentration to the power C, this concentration to the power D, divided by this concentration raised to the power small b, and this concentration raised to the power small a. That is Kc. But other than Kc, at this moment also you can write like that: C to the power C into D to the power D divided by D to the power D into A to the power A. But that is not Kc value. Expression format is the same. That expression, we write it as QC reaction quotient at that particular time. At that particular time. And what about this? This is another QC, another C to the power C, this concentration, but it is not at the equilibrium, other than the equilibrium, before reaching this equilibrium. C to the power C into D to the power D upon A to the power A into B to the power B. Expression format is the same, but it is not Kc. We will be writing again QC. So there can be so many QCs, but only one Kc. Now you see, in Kc here, C amount is more, D amount is more. Here, C amount is less, D amount is less. These are coming in the numerator, right? So QC value will be lower than this Kc value. Here numerator has got more amount. In this particular case, QC is less than Kc. Even this QC is also less than Kc, because this C amount and this D amount is less than this C amount and this D amount. Here also, accordingly, this is more and this is more compared to this and this. So denominator will be bigger. Denominator is having a bigger value. Numerator is having a smaller value as compared to this case. So QC, this is at any time. Suppose this is 0 time started. After 5 minutes, after 10 minutes. When it reached 15 minutes, equilibrium is attained. So at 5 minutes and at 10 minutes, what you write, the same format, that is QC. At 15 minutes, what you are writing, that QC is equal to KC. That QC, here what? Here also you can write QC, but that is equal to KC. So when QC is smaller than KC or QC is less than KC, the reaction will proceed to the forward direction. Anyway, QC will try to reach KC. QC means we call it as reaction quotient. KC is equilibrium constant. At equilibrium, QC will become equal to KC. Otherwise, at any other time, means after this also it is QC only. How? If you add some products into this, then they will move back to form the reaction. That time QC. When you add little more C and little more D to this, then what will happen? Numerator will be very high. Numerator will be very high. Then QC value will be very high. So QC will try to reach KC by how? By moving towards the backward direction. Anyway, QC will try to reach KC. If QC is less than KC, the reaction will proceed in the forward direction. If QC is greater than KC, then the reaction will proceed in the backward direction. So you write one numerical for that. The value of Kc for the reaction, the value of Kc for the reaction 2A equilibrium B plus C is 2 into 10 to the power minus 3. 2 into 10 to the power minus 3. Right? At a given time, the composition of the reaction mixture is A is equal to B is equal to C. All compositions are same here. This is an instant, a particular instance. That is 3 into 10 to the power minus 4 molar. In which direction the reaction will proceed? In which direction the reaction will proceed? In which direction the reaction will proceed? So at a particular time, this is the concentration. So I'll be finding out QC. QC is equal to B into C upon A square, A to the power 2. What is B? Same. 3 into 10 to the power minus 4. C. A. So all get cancelled. So this is 1. This is 1. So QC is equal to 1. What is KC? This is 2 into 10 to the power minus 3. Which is greater? 1 is greater. So QC is greater than KC. The reaction will proceed in the reverse direction. So the answer is QC is greater than KC. QC is greater than KC. That means the reaction will proceed in the reverse direction or backward direction. So that is how. QC means at any time. Kc means at equilibrium. The third one is one more question you write. In a reaction at 700 Kelvin, in a reaction at 700 Kelvin, molar concentration of H2 I can show like this. At any time t, molar concentration of H2 at any time t is equal to zero point 0.1 molar. 0.1 molar. I2. At any time t means we are going to see QC is equal to 0.2 molar and that of HI 0.4 molar. In which direction the reaction will proceed? In which direction the reaction will proceed? In which direction the reaction will proceed? So I'm going to find out QC. Kc value, we have already learned Kc value is 57 for this reaction. Kc value, I am writing Kc value 57. This will be given in the numerical Kc value. You cannot by heart all the Kc values for different reactions. Kc value is 57. Now let's see the QC. QC is equal to, that is H2 plus I2 gives 2HI. H2, H2, equation is H2 plus I2 gives 2HI. So QC I am going to find out HI square, that is 0.4 square divided by H2, 0.1 into I2, that is 0.2. So you are getting it as 8. The value you are getting it as 8. QC. QC is calculated in the similar way as that of Kc, but the consideration will be different. In Kc, this concentration will be only equilibrium concentration. So QC is 8. What is Kc for this reaction? 57. So QC is small, the reaction will proceed in the forward direction. The reaction will proceed in the forward direction. Now, third one is calculating this equilibrium concentration. Calculating this equilibrium concentration, we have already said in the previous day we did one numerical, and in that we calculated the equilibrium concentration. Calculating the equilibrium concentration means, for example, I am giving a decomposition reaction PCl5, PCl3, and Cl2. We have started the reaction. PCl5 amount is getting reduced, and PCl3 and Cl2 concentrations are getting increased, and finally it will be coming to an equilibrium. It will be coming to an equilibrium. At equilibrium, what are the concentrations of these three species? PCl3, Cl2, and PCl5. Suppose at equilibrium, if they are giving the concentrations, write down the question. 3 moles of PCl5 kept in 1 liter closed vessel. 3 moles of 3 moles of PCl5, 3 moles of PCl5 kept in 1 liter closed vessel. 1 liter closed vessel was allowed to attain equilibrium at 380 Kelvin. Equilibrium at 380 Kelvin. That means it is heated. Heater means decomposition is taking place. So you should write a decomposition equation. Like this, PCl5 decomposes to form PCl3 and Cl. Calculate the composition of the reaction mixture. Calculate the composition of reaction mixture at equilibrium. Calculate the composition of reaction mixture at equilibrium. So in the beginning, I have taken 3 moles in 1 liter vessel. In 1 liter vessel, 3 moles I have taken. So in the beginning, 3 moles. And heat it. 380 Kelvin is temperature I am giving. So in the beginning, it is 0 and 0, no product. After some time, when the equilibrium is reached, we don't know how much bond that side. So I'm taking it as X. So what is remaining? What is remaining in this PCl5? 3 minus X. Now you see, if one goes, one this thing will be formed, one this thing will be formed. If X goes, X this thing will form, X this thing will form. So this is X and X. We don't know the value of X. जितना जा रहा है उतना वहां दिखेगा. So what is Kc? Kc is equal to X into X upon 3 minus X. 3 minus X. That is Kc value. Kc value is given in the numerical. Kc is equal to 1.8. Kc is equal to 1.8. So this is 1.8. Kc is equal to 1.8. You have to solve this quadratic equation. So 1.8, you have to solve this quadratic equation. It is very difficult to solve the quadratic equation. So x square plus 1.8x, it will be x square plus 1.8x minus 5.4. 5.4 is equal to 0. So you have to solve minus b plus or minus square root of b square minus 4ac upon 2a. In that way, you have to solve this. Solving is difficult. I am giving you the x value. I am giving you the x value, that is 1.59. 1.x is equal to 1.59. That means what is the composition in the equilibrium mixture of PCl3? 1.59. What is the composition? 1.59. What is the composition? That is the remaining PCl5. 3 minus 1.59. That is 1.41. So this will be 1.59. Then the 1.59. This will be 1.59. And this will be 3 minus 1.59, which is equal to 1.41 molar. So these are the concentrations of different species in this equilibrium. So that is a third application. So using this equilibrium constant only, you can calculate these things, equilibrium concentrations. So these are the applications of equilibrium constant. Thank you.